Hello and welcome to part 2 of a short mini-series on polynomial division. In the last video, I discussed the method for the algorithm that enables us to long divide polynomials. In the process of long division, we learn if we have a remainder of 0, just like with regular numbers, we have factors. So basically, in this case, x plus 1 divides evenly into x squared minus 9x minus 10, and that's x minus 10 times. Just a quick review over here, you can see instead of using the division algorithm, I could achieve the same result by using quadratic factoring skills that I may have learned in previous classes. Another quick reminder is this is an alternative way of expressing the quotient. So this is basically it would be a number like 24 divided by 6 equals 4. So we have that, or we could say 24 equals 4 times 6. So each of these expressions is a truth that results from either the division or the factoring process. Anyway, further developing these ideas, I wanted to look at perhaps, hold on a second, make sure, yeah, I got the right one. I wanted to look at perhaps if there's a better way to do this work, because as you can see in this demonstration, I just divided a quartic polynomial by a linear divisor. And in the process, I ended up with a cubic polynomial with a little bit of a remainder left over, and all of this follows the same algorithm that was discussed in part 1 of the video series. But what I'd like to do is to demonstrate a shortcut algorithm that people more clever than I discovered. And what they discovered was the x to the 4th, x cubed, etc. These are just placeholders, and they really don't develop the algorithm in any other way except for holding place. And the idea is that in the process of the algorithm, we're repeatedly multiplying, and subtracting, and so forth. Interestingly enough, what I'm ending up doing, well, never mind, I'll get to that in a second. So here's what somebody noticed. They noticed that if I just use holding place values without the x's and just keep everything in order, we imply x to the 4th, x cubed, and so forth as we go down the chain here. So we're going to take the coefficients of the divisor, or the dividend, sorry. I'm going to take the coefficients of the dividend, and then I'm going to take the 0 of the divisor, and this hopefully becomes more clear later, but basically I'm going to take the opposite of this number right here, but that's not always the case, but for now let's just do that. Since I'm taking the opposite of this number right here, instead of subtracting repeatedly in this algorithm, I'm going to add repeatedly. So I'll show you what you do. The algorithm says, let's drop the 1, multiply the divisor number, that is the 0 of the divisor, by 1, so 3 times 1 is 3. We bring it up to the next slot. Then we add the 4 and the 3. So what I was trying to say earlier when I was stammering over there was this is -3, this is +3. Here I'm subtracting repeatedly, here I'm going to add. So we're kind of like undoing and then redoing a process. That's kind of a really loose way to think about it, but it's the way I kind of keep it straight in my head. Anyway, 4 plus 3 is 7. Now we're going to multiply 3 times 7 to get 21. 21 plus -8 is 13. And 13 times 3 is 39. 39 plus 0 is 39. And finally, 3 times 39 is 117. And we add 3 plus 117 to get 120. As you can observe, each of these numbers in the part of the algorithm is represented along this bar. Furthermore, each of the coefficients on my quotient end up being the coefficients represented down here, including the remainder in the box. So basically, this is an elegant shorthand so we don't have to dig through all those extra variables. Be warned though, this shorthand only works when dividing by a linear factor. If we're dividing by anything like a quadratic or higher, this algorithm falls apart. So sometimes people don't use it. Now I'd like to discuss briefly another discovery, and that is when I evaluate f of 3, the function that is the dividend, that would be the numerator, if I evaluate the numerator at 3, doing the old-fashioned substitute and evaluate, I get 120. So the question is, what's going on there? And that introduces the concept known as the remainder theorem. What the remainder theorem is saying is we can achieve evaluation of a function in one of two ways. We can evaluate the function at the zero of a supposed divisor, or we could just straight up divide to get that same remainder. So what's the big deal? What's it for? Well, I got to tell you the truth. It's kind of an obsolete algorithm, but IB likes to use this algorithm as a way to sort of demonstrate how to apply a fact to a problem, so we can learn more about problem solving. But another important thing about the IB way is not just accepting at face value everything you're seeing. For example, let's see if I got the good example. There it is. When we did the long division right here, I got a remainder of 2, which is why I was able to conclude that f of 2/3 is equal to 2. Notice that 2/3 is the 0 of the divisor. If we set the divisor equal to 0 and solve, we'll get x equals 2/3. So why does the remainder theorem work? The answer is by understanding that the numerator can be expressed as the product of the quotient times the divisor plus the remainder. If we substitute the 0 of the divisor into the divisor, we get 0. That sounds like circular talk because it is. 0 times who cares is going to be 0, and we'll be left with the remainder straight up, yo. Now this happens to be sort of useful in the back end, and when I say obsolete, because back in the old days, people didn't have calculators to do their work for them. So when faced with having to evaluate a polynomial this way, they might have a little bit of trouble taking things to the 4th and 3rd powers, not in the case of 3, but in the case of some more ugly numbers. So as an alternative to doing function evaluation, they just apply synthetic division, and they can get the value of the function at 3. What IB does is they actually they flip that process, and that's going to be revealed in part 3 of this series on polynomial division. So in the first part of the series, I talked to you about long division. The second part of the series, I talked to you about synthetic division as a shortcut, only when dividing by linear factors, and that leads us to this thing called the remainder theorem. I'm going to show you how IB uses the remainder theorem in the third part of the series. Thanks for watching.